Hey, what's up, Algebra 2? It's Ryan. Today we're going to be going over radicals and rational exponents, which is a hallmark topic in the Algebra 2 curriculum. It's going to show up in pretty much every single Algebra 2 class you take. So it's a really important topic, and it's really important that we get this under our belt for future math classes, and hopefully by the end of this lecture, we take the first step in really mastering this subject. Okay, so let's get started. First, we have this warm-up, and we want to talk about perfect squares. So squares mean numbers that when we multiply one number by itself. So essentially, we have 1 times 1, which is 1. We also have 2 times 2, which is 4. We have 3 times 3, which is 9. 4 times 4, or 4 squared, is 16. We have 25. And we can keep on going. Okay. So this is 8 squared is 64. 9 squared, 10 squared. And we can keep on going. Okay, I'm just going to stop there. Okay, then we have cubes. So actually first note about the squares, perfect squares. You should probably, it would be helpful if you have all your perfect squares memorized up until at least 144 or 12 squared. If you can go all the way to 20 or 21, that would be ideal. Okay, so now we have perfect cubes. So cubes means numbers that when we multiply it by itself 3 times. So essentially we do 1 times 1 times 1. That's going to give us 1. 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. 4 times 4 times 4 is 64. 5 times 5 times 5 is 125. 6 times 6 times 6 is 216. 7 times 7 times 7 is 343. And you can keep on going. Okay? Then we have perfect fourths. So this is going to be numbers that we multiply by itself 4 times. So we do 1 times 1 times 1 times 1 is 1. 2 times 2 times 2 times 2, 16. 3 times 3 times 3 times 3 is going to be 81. 4 to the fourth is going to be 256. 5 to the fourth is going to be 625. And that's probably a good place to stop. Okay? So just as we go through this unit, you'll be more comfortable with recognizing some perfect squares, perfect cubes, and perfect fourths. And that's just going to help your overall fluency, numerical fluency, and just recognizing sort of how to simplify a radical or how to rationalize something. And you can just work quicker. Okay, so let's talk about parts of a radical. When we have the nth root of a real number, a, it can be written as the radical expression here. So we have this radical, that's this sort of line. So this is called the radical. Okay? Radical. And we have this number up here. And that n is going to be our index. So essentially what our index is doing is it's saying what number root. of A. Okay, and I'll talk about that more in a second. A is going to be our radicand. Okay. So essentially what the index is doing, if we have, for example, the second root of 4, we're looking for a number when multiplied by itself 2 times gives us 4. So that's going to be 2 times 2. Or conversely, sorry, my bad. Or conversely, negative 2 times negative 2. Okay? So, sorry, I just got to turn off this alarm. So this is going to be positive or negative 2. So this would be equal to, there isn't really a good way to write that down, but you get the idea. If it was, for example, the third root of 27, we're looking for a number when multiplied by itself 3 times gives us 27. So that's going to be either, that's just going to be positive 3, because 3 times 3 times 3 is 27. Okay? And we're getting, in this case, maybe it's not a great example, but we're multiplying 3 by itself 3 times to get 27. And that's where we get this index. Okay? Now, in the example before, I said the second root of 4. We would not really say that, because when we don't have, or when we're doing the second root or the square root, we just don't write the index. So if there's no index, it's assumed that it's a square root, which essentially just means n equals 2. Okay, so let's move on to the number of roots. Okay, so the square root of 16, remember we don't have an index, so we assume that it's 2. So we're looking for a number when multiplied by itself 2 times gives us 16. So that means we're looking for a number, let's just say x times x equals 16. And that's going to give us 4 plus or minus 4. Because 4 times 4 is 16. Negative 4 times negative 4 is 16. Here we're going to have plus or minus 11, because 11 times 11 is 121. Negative 11 times negative 11 is 121. Here we can say plus or minus 17. Now, if you don't know what the square root of 289 is, you can sort of guess. You can see that it ends in a 9. So you're looking for a number when multiplied by itself also ends in a 9. So like, for example, 7 times 7 is 49. So that ends in a 9. So you know 17 squared is going to end in a 9. And you can sort of validate it by multiplying 17 times 17. Here, in this case, the square root of 4/25. If you remember back to last unit, we can write this. One of our exponent rules is we can write this like this, where we have 2 radicals. And in this case, the square root of 4 is 2. And the square root of 25 is 5. And we'd put a plus or minus out in front. Okay, great. Now let's move on to cube roots. So the cube root of 8 means we're looking for a number when multiplied by itself 3 times gives us gives us 8. So that means x times x times x gives us 8. That's going to be 2. And right, this is just remembering what we did up here, right? 2 cubed is 8. Okay. 343, the cube root of that is going to be 7. Now, or 1 second, I'm going to do one more, then I'm going to make an important note. Or, you know what, I'll just make the note right now. Up here, I put plus or minus because, for example, we could do 4 times 4 is 16, and negative 4 times negative 4 is 16. However, with cube roots and any odd number roots, we can't do that plus or minus. Because, for example, if we were to do negative 2, negative 2 times negative 2 times negative 2, I should write this out different, but you get the idea, is going to be, well, negative 2 times negative 2 is 4. 4 times negative 2 is now negative 8. And that's not equal to 8. Okay? So this is only positive. Now, if I were to ask for the cube root of negative 8, we would say negative 2, which we just proved, right? We sort of went that way, and now I'm just going backwards. Okay? So, for example, over here, when we're asking for the cube root of negative 125, we would say, well, first think, what's the cube root of 125? That's going to be 5. But since there's a negative sign out in front, we need to put a negative sign outside of this, because negative 5 times negative 5 is 25. And then we have to multiply by negative 5 again, because it's a cube root. So 25 times negative 5 is going to give us get us to that negative 125 mark. Okay? Perfect. Now, again, we can sort of split it up like we did in the last unit and have the cube root of negative 1 up there, the cubed root of 27 down here. Now the cube root of negative 1 is just going to be negative 1. The cube root of 27 is going to be 3. Okay, great. Now the fourth root would be when we, the numbers, a number when we multiply by itself 4 times what we get. So, for example, the fourth root of 1 is just going to be 1. Now the fourth root of 2,401. Now, to be honest, I don't know this off the top of my head, but I'm going to look at it and think there's no way it's going to be 2. There's no way it's going to be 3, something low like that. We went all the way up to 5 here. So 5 to the fourth is going to be 625. So I know it's going to be greater than that. I'm going to plug in something like, let's do 8. Okay, 8 to the fourth. Now I have a calculator out here, and you can actually multiply it out yourself. That's what you'd probably do, just test a bunch of things and do multiplication. But 8 to the fourth, I'm getting 4,096, which actually gives us our answer over here. So I'm going to write that in right now. And this is going to be plus or minus again because it's an even root. And if I were to do positive 8 times positive 8 times positive 8 times positive 8, I get 4,096. If I were to do negative 8 times negative 8 times negative 8 times negative 8, I also get positive 4,096 because we have 4 negatives, and that means those essentially cancel out. Okay, now we're still thinking about that 2041. Let's try 7 to the 4th. And that does work. So we're going to say 7, or plus or minus 7. Now, one thing you can do is for fourths, like for example, 7. You know 7 squared is 49, okay? So 7 squared, maybe I write this off to the side. 7 squared times 7 squared. If you remember your exponent rules, we would add the exponents when we have the same base. Or sorry, not 2 plus 4, 2 plus 2. So this is equal to 7 to the 4th, okay? So if I go backwards, 7 squared is going to be 49 times 49. And you can just do your multiplication that way. And you notice if we take the ones place, 9 times 9, that gives us 81. And since that ends in a 1, 2041 ends in a 1, you might be able to assume, and like 7 would be a good guess. Okay? Yeah, so sometimes math is about guessing, or knowing how to guess correctly. Make an educated guess. Okay, so the 4th root of 81 over 16, this is going to be the 4th root of 81 over the 4th root of 16. Now, if we look back up here, we essentially said the 4th root of 16 is going to be 2. We said the 4th root of 81 is 3. So we're getting 3 halves. Again, it's an even root, so we need to put a plus or minus out in front. So just as a reminder, when we have an even index, an even root with a positive radicand, so essentially a positive number under the radical, we're going to have real roots where we have 2 from that plus or minus. When we have an odd I don't know if when they say type of roots, they mean real or positive slash negative. I'm going to say real and positive slash negative. Now, when we have an odd index with a positive radicand, we're going to have a real root with, or that has a positive sign. So 1 root. Here, when we have an odd index with a negative radicand, we're going to have a negative root. We're only going to have 1. So, for example, the cube root of negative 125, we only have 1 answer, and it's a real negative number. Now, when we have an even index with a negative radicand, we don't have a real root. We have an imaginary root. Okay, think taking the square root of negative 9. We went over this earlier this year, and that would be 3i. We can't take the square root of a negative number, and we can't take the 4th root of a negative number, or we can't take an even root of a negative number. Okay? So this would be 0 real roots. Okay? And maybe you can say plus or minus 3i, but those would both be imaginary. Okay, so now let's move on to simplifying radicals. So maybe you've done this in past math classes, but this is going to be something that's super important as we move forward. So how I want you to approach this is look at the number under the radical, the radicand, and try to find some perfect square factors of that. So for example, we're looking at 117. 1 isn't going to be helpful, but is 4 a factor of 117? No, probably not. Is 9 a factor? Let's think about this. 9 times 10 is 90. 9 times 11 is 99. And then from 99 to 117, we have 18 more. And 9 goes into that 18 twice, evenly, perfect. So we're going to split this up. So essentially, we find out that 9 times, 9 times 11 is 99. Then we need 2 more to get us to 117. That's equal to 117. So 9 times 13 is 117. So how I want you to rewrite this is square root of 9 times square root of 13. Okay, now what's the square root of 9 equal to? That's just going to be equal to plus or minus 3. And then we still have that times root 13. And we do that. Now, can we simplify root 13? Does that have any perfect square factors? No, it does not. So this is going to be our answer. Okay, let's move on to number 3. And we're not going to do all of these problems. This is going to be a long packet, but we're just going to get started. Okay? So we have 2 times the cube root of 48. So first, let's think of some perfect cubes that may be a factor of 48. So for example, we have 1, which is helpful, and then we have 8. Is 8 a perfect cube factor of 48? Yeah, because 6 times 8 is 48. So, and remember 8 is a perfect cube for 2. So I'm gonna rewrite this as 2 times, and then I'm gonna split up 48 into the cube root of 8, and then the cube root of 6. Sorry, don't mean to put 6 there. The cube root of 6. And that's gonna give us 2 times. Now the cube root of 8 is going to be equal, the cube root of 8 is going to be equal to 2 and only positive 2. And then we're still going to have the cube root of 6. So this is 2 times 2 is 4 times the cube root of 6. And that's going to be our answer. Okay? So that's how you want to approach these sorts of problems. Find the perfect square factor, rewrite it out, where our radicand is going to be separated into our perfect square factor times whatever is left over, and then evaluate the perfect square factor and sort of simplify. Okay, now let's move on to radicals with variables. So square roots, exponents must be multiples of 2. Okay. For cube roots, exponents must be multiples of 3. For fourth roots, exponents must be multiples of 4. And you're going to sort of see what I mean here in a second. Okay, so now that we've introduced variables, everything is pretty much going to say the same, with at least the constant part of it, this coefficient. So we want to find, for the 32 part, we want to find the perfect square factor that goes into 32. And we want the greatest perfect square factor. And that's going to be root 16. So I'm going to say root 16 times root 2, since 2 is left over. 16 times 2 is 32. Okay? Now, I'm going to separate this. I'm going to say times root x to the 4th. And then I'm going to say times root y to the 9th. Okay? So, x to the 4th, or the square root of x to the 4th, what that's doing is that's essentially dividing our exponent by 2. That's what the square root is doing. So 4 divided by 2 is 2. So we're going to say that's equal to x squared. 9 divided by 2, well, that's going to be 4.5. So this is going to be y is equal to 9.5, or 4.5. Now, we would not really say something's raised to the 4.5 power, but I'm going to show you something here. Y raised to 4.5 power. Sorry, that's really wonky. That's going to be equal to y raised to the 4th times y to the 1/2 power. Okay? Because we have the same base and we're sort of working backwards from our exponent rules, if we were to, since we're multiplying, we would add these two exponents and we get 4.5 or 4.5. Okay? So now we can just say y is equal to 4. We can also say when we raise something to the 1/2 power, that's going to be equal to the square root of y. We're going to be talking about that a little bit more later. So this root y to 9th is equal to y to the 4th times y, or root y. So now we're at the point, and I'm going to write this out here. 16, or the square root of 16 is plus or minus 4. And then I'm going to say times the square root of, or times x squared, which we got up there, and times y to the 4th, which we got down there. And this is still going to be multiplied by root 2 times root y from here and here, respectively. And that's just going to come out to, we're going to have the same first part, 4x squared, y to the 4th. And then when we multiply root 2 and root y, we can just say root 2y. Okay? Something like that. Now, there's a bunch of different ways you can think about this. You don't necessarily have to think about it where you're raising something to the 4.5 power and separating it like this. That can be sort of wonky to think about. Maybe what works best for you is we have something with this when we don't have an index. So that means we sort of have an invisible 2 right here. Okay? What you want to think about then is for these variables, how many times can 2 go into our exponent 9 without going over? Evenly without going over. Or, sorry, not evenly. How many times can 2 go into 9, the greatest amount, without going over? Well, it would go in 4 times, and we'd have 1 left over. So we would say y to the 4th, because we have y squared from this 2, y squared going into y to the 9th 4 times evenly. And then we'd have 1 y left over, or a y to the 1st. And so that's where we would still keep that under the square root, if that makes sense. So how about this? Let's try to implement that now. into a question like this. Number 13. So we're asked to find the cube root of negative 64. So the cube root of negative 64, we actually went over this before, that's going to be equal to negative 4. And only negative 4, because we have this negative side, it's an odd root. Okay? Now, what we want to do is we see our index is 3. So for this x part, we're asking ourselves how many times can 3 go into 10 without going over? And that's 3 even times. So we're going to say x to the third. But when 3 goes into 10 3 even times, that gets us to 9. And then we have 1 left over. So we still need to multiply by the cube root. Sorry, it's kind of hard to see. The cube root of x. Now for the y part, we're asking ourselves again, how many times does 3 go into 21? That goes in 7 even times. There's no leftovers. So we're going to say y to the 7th. Okay? And from here, we're just going to simplify, write it out again, and we get something like this. Sorry, this is like x. And that's just going to be our answer. Okay? Great. So let's keep on moving on. Let's go to adding and subtracting. Adding and subtracting radicals. So there's some rules. First, simplify all radicals, and then identify radicals with the same index and the same radicand. Okay, so the same number up here above the radical and the same number below. And then for the common radicals, we want to combine them. So add and subtract the coefficients, but keep the common radical. So for example, let's try to simplify 3 root 27. Okay, so I'm going to write that over here. 3 root 27. Well, the square root of 27. So let's think of some perfect square factors. We have 4. 4 isn't going to be a factor of 27. Then we have 3 squared, which is 9. 9 is a factor of 27. So we're going to write 3 times root 9 times, and what do I need to multiply 9 by to get to 27? Root 3. Okay? Now, the square root of 9 is equal to plus or minus 3. So I'm going to switch these two. I'm going to say plus or minus 3 times 3 times root 3. And this is going to give us, actually in this case, we would not really say plus or minus 3. We would assume, since this is an expression, we would assume that it's equal to 3, okay? That's an important note. So we would have 3 times 3 times the square root of 3. So that gives us 9 root 3. Now for 2 root 12, we have 2, and then what's perfect square factors of 12? Well, we have 4, and 4 is a factor of root 12. So we say times root 4, and then we need to multiply by root 3 because 4 times 3 is 12. So this gives us 2. Then the square root of 4 is just 2, and then we multiply by root 3. So this gives us 4 root 3. So I can rewrite this equation as 9 root 3 minus 4 root 3. Now, we have the same common radical, root 3, with the same index, which is 2, and the same radicand, which is 3. So now we just want to subtract the coefficients. So 9 minus 4 is 5. This gives us 5 root 3. We keep that common radical. Okay, let's do something. Let's do number 5. Okay? So for example, number 5, we have root 98. Well, root 98, let's think about some perfect square factors of that. We have 4, which is not a factor of 98. We have 5, which isn't going to be a factor. We have 6, which isn't going to be a factor. We have 7, which is going to be a factor. Because, or wait, no. Yeah, no, it is. Sorry. 7's going to be a factor. Or, sorry. What I mean is, when I'm saying 2, 4, 5, whatever, I'm thinking of the square of that. So for example, 4 isn't a factor, but we have 16, or sorry, 4 isn't going to be a factor. Is 9 going to be a factor? No. Is 16 going to be a factor? No. Yeah, I don't believe so. Yeah, no, it isn't. Is 36 going to be a factor? No. I missed 25. Sorry, it's early in the morning. My brain is not fully clear yet. 25 isn't going to be a factor. 36 isn't going to be a factor. 49 is going to be a factor. So that's going to be where I was talking about 7. I can write cube or square root of 98 as root 49 times 2. And then I'm going to say times. Now, this has an index of 2 since we can't see it. How many times does 2 fit into 4? Well, it fits in 2 times without going over. And so we're going to say x squared. And there's no leftover. Okay? So it's just going to be the square root of x to the 4th is just going to be x squared. That's what I'm saying. Now, in the same sense, we're taking the square root of y squared. That's just going to give us y, right? Because we're saying how many times does 2 fit into 2? That's 1 time without going over. There's no leftovers. Now, at this point, the square root of 49 is 7. And now I'm just going to rearrange this. I'm going to say 7x squared times y times root 2. Okay, now let's do the 3x squared y root 2. Or, no, it's already the right form. So we have 7x squared y root 2 minus 3x squared y root 2. Well, I noticed this common term, x squared y root 2. What if I were to rewrite this equation as x squared y root 2 times 7 minus 3. Essentially just factor out a x squared y root 2. That would give us 7 minus 3 would give us 4. So we'd basically say x squared y root 2 times 4. It's going to give us, it's going to be this expression simplified. So I'm going to put the 4 out in front. Doesn't matter where you put it because of the associative property. So we're going to get 4x squared y root 2. And that's going to be our final answer. Okay? Great. Now, one last thing, let's talk about multiplying radicals. When we multiply Well, when multiplying radicals, we first want to multiply the coefficients, and then we want to use the product rule. This essentially just says the nth root of a times the nth root of b is going to give us the nth root of a b, or a times b. We know because we've been doing this before. When I break up, for example, root 12 into root 4 and root 3, that's going backwards, okay? And so now we want to, the second step in multiplying radicals would be simplifying the resulting radicals. So we want to multiply 27 and 5. So let's see. Let's get our calculator out. You would actually do this on paper, but I'm just going to use a calculator because it's faster. Okay, so 27 times 5 is 135. So this is going to be equal to root 135. Now, we want to think of some perfect square factors of 135. So, is 4 a factor of 135? No. Is 9 a factor? Let's think about it. Well, we have 9 times 10 is 90. And then we have 45 left until 135. And 45 is a multiple of 9. So 9 does go into 135. Let's see how many times. So we have 9. Then we said 9 times 10 is 90. And then we have 45 left over until 135. 9 goes into 45 5 times. So we can say 9 times 15 is 135. Okay. Now we can simplify and say that this is equal to 3, since the square root of 9 is equal to 3. We can say that's equal to 3 root 15. Now, at this point, we'd want to look at a radicand 15 and see if we can simplify that anymore. We can't. There's no perfect square factors of 15. So, that's our final answer. Okay. Now let's do number 10. So we first want to multiply the coefficients. And our coefficients are -3 and -1. Right, when you have this negative sign out front, that's essentially like saying -1. -3 times -1 is just going to give us +3. So I'm just going to write that as +3. Now, we can multiply these out, 64 and 8, and try to find the fourth root of that. I would go a different route. You know what? No, we have to. Okay, never mind. Let's do 64 times 8. Sorry, I'm a little bit discoordinated. Okay, 64 times 8, that's going to give us 512. The fourth root of 512. Okay, so now let's go back up to the very beginning. We keep 512 in our brains. Are any of these perfect fourths factors of 512? Well, we see 256, which is half of 512. And 256, by the way, is 4 to the fourth. So what we want to do is we want to say that this is equal to 3 times root, or fourth root of 256 times the fourth root of 2. Okay? And now the fourth root of 256 is going to be equal to 4, as we just said. And so that's going to be 3 times 4, which is 12, times the fourth root of 2. and that's going to be our final answer. Okay, so there's still more to come. We're going to be talking about some more on radicals and rational exponents, but this is just going to be part one. Right now, if you have any questions about how I did any of these problems, go talk to your teacher, go to the tutoring center, certainly reach out to me and use the internet as a resource, and stay tuned for part two. Okay, see you later. Bye.